Okay, so we're not quite done with limits, but we're going to segue into a different topic where we're going to use limits to talk about that topic. And so your quiz today is on limits, which you'll have later. But today, we are going to talk about a topic called continuity, of course, of functions. So to start with the mathematical definition, there's a more in-depth one than this, but this one is a good place to start. Give the math definition first, I'll tell you a little bit more about the intuitive definition afterwards. A function f of x is said to be continuous at a point x equals a. If the following equation holds. So I am defining the word continuous, but there are two main types of continuity. So more specifically here, I'm defining what it means to be continuous at a specific point, at a point where x equals a. I mean, x equals a is not a point, but let's say where the x coordinate is a, and we say a function is continuous at a point where the x is a if the following equation holds. If the limit, does anyone know what the equation is? Anyone remember? Continuity defined as an equation. If the limit as x approaches a of f of x is f of a. In other words, the same kind of function where our plug-in rule would work without doing anything crazy, such a function is continuous at a point. So at specific points where the x-coordinates are a, I can talk about a function being continuous there. It just means that the limit as I approach the point is actually equal to the output value of the function at that point. This can be contrasted with something like continuous just in general. So you can talk about continuous at a specific point, or you can talk about being continuous in general. So when someone says continuous at a point, they mean this equation holds. If we say a function is continuous, it means this equation will hold not just for the specific point A, but it will literally work for all x values in the domain of the function. So it's kind of like you can apply this equation at any point and it will work. Right? So what does this actually mean? Here's the intuitive interpretation. This means f has no holes, gaps, jumps, breaks, etc. in its graph. Right? So in theory, you can draw the picture of f without ever lifting your pencil off the page. You'll just keep going and you never have to worry about jumping over something or having to create a hole or do a break or anything like that. It turns out that in the case where f has this property, this equation is going to hold. Right? So let's look at some illustrations here. And see how this equation can break. So here are some examples of situations where we are not continuous at the point A, and we're going to explain that looking at this equation can actually describe all these situations and tell you whether or not they will work or not. So one, again, this is going by an example that we've kind of seen before, where a function seems to be okay except for a single point with a hole in it. For us, this would not be continuous because there's a hole, there's a gap, there's a break, there's a point where you can't draw it without lifting your pencil off the page. You have to jump over this point and continue. Okay. Another situation is maybe it's not completely undefined at that point, but maybe some other point is filled in. So this means your f of a is somewhere else, away from your function. You still would have to lift your pencil off the page to draw that and put it back and continue. There are more drastic things that can happen, like that, right? You'd literally have to make a jump to go to the other side. Or that. And let's assume this is all happening at A. You could also have something like this. Say that's A, the function is doing that. You can do the other side of that as well. So something like this side is filled in, but that side isn't. So here are examples of functions that you can draw, which obviously, in the intuitive definition, they don't continue. They're not continuous. There's a break, there's a jump, there's a gap, there's an asymptote. Things aren't working out smoothly, let's say. And if you start to examine these things in terms of limits approaching the point and the value of the function at the point, you'll notice here, does the limit here exist? Does it exist? Yes, the limit here exists. Right, so it's equal to some value, say L. But what is the value of the function at that point? There is no value of the function. It's undefined. Right? So it's a break. Right? If you look at this situation, the limit does not exist. Although f of a is defined, it's equal to, let's call it b, where that's the value. In this case, again, limit does exist. In fact, the limit is going to be L, which is right there. F of a is defined. However, f of a is defined, let's say at b, but your L is not equal to b. So even though both of them are working out, they don't agree. The equation that I had here that I erased is not going to hold. Here, both actually break. The limit does not exist. And the function itself is undefined. If you look over here, in theory you can say the limit is infinite. It doesn't really exist as a real number, so one thing to note is that's not a real number. It's not even a number actually. But more importantly, f of a is undefined. So the equation is going to break as well. Here, limit does not exist, even though f of a is defined to be c. So if we're looking at these two quantities, the limit and the value of the function, the limit and the value of the function, the limit and the value of the function, at any time we can compare these two quantities. right? If one doesn't give us an answer, then obviously they can't be equal to each other. This gives us a number, that one doesn't. In this case, this doesn't give us a number, but that one did, right? So there's no hope of them being the same, and there's a break in the picture. Here, both actually existed on their own, but they didn't agree with each other. So obviously now there's a break in the system, right? So the curve at every point except A, everything is fine and dandy, but at A, there's a jump to some other point, there's a disconnection. Here, both of them just don't work. Here, one kind of works, but it's not even a real number, but the other one doesn't work either. Here, the limit works, but the function works, but the limit doesn't. So you can see in all these situations, you would have a break, a gap. Something bad is going to happen that you can't just draw out the function and not worry about it. There's some sort of situation at that point that makes it discontinuous. Okay? If you contrast that with what you can intuitively think of as a continuous function, so at some point A, if you want your function to be continuous around this, you would intuitively, I should be able to just draw the function and not worry about it. No gap, no jumps, no breaks, nothing to worry about. And then you can start to examine this point, f of A, which is going to be defined, and you'll notice that f of A is defined. You'll also notice that the limit as x approaches A of f of x exists, right? Because as you're approaching from the left and the right, the y-coordinates are converging to the same number, and they're actually the same value. Now once that works out, literally means you can draw the function without lifting your pencil off the page, because all your y values are converging to the same point, and on top of it, that point is actually filled in. So you don't have to jump over it. You can just pass right through it, and you will still be in the function, the output of the function the whole time. Right? So this is one situation in which mathematicians took a very intuitive idea that you can see on a picture, and they make it very precise, concrete mathematical fact. You don't even need to know what the picture looks like, just check this equation. If this equation works out, the picture is something you can draw without lifting your pencil off the page. If the equation does not work out, it's not, right? And that's it. So you don't even have to know necessarily what the graph is look like, just know how to find a limit, and you can talk about how the graph will behave. And I'm just drawing some pictures here to illustrate to you what's going on, but the idea is this equation is a very powerful equation when it comes to talking about the behavior of a function at a certain point and whether there's a break or a gap or a jump or something at that point. Now, continuity is important because, as you'll see, when there's a break or a gap or a jump, we can't really do calculus at that point. Calculus is going to work at the other points, but it won't work at that point. And so, if we're studying a calculus class, we'll want to know in what situations we can actually use calculus. It turns out that in the situations where there are breaks or jumps or gaps, we can't. And we should want to know that and know where these points exist. So, does everyone kind of get the idea? Okay. So the idea of continuity is that you should be able to just draw the function, no gaps, no breaks, no jumps. How do you know mathematically or algebraically if that will work? Even if you don't want to draw the graph, check this equation. I also want to note you should know that three things need to happen here. One, f of A must be defined. Two, the limit as x approaches A of f of x must exist. There are some notes that we can talk about here. Where's my page? There are some notes that we can talk about here. It is understood that it must be a finite number. It should also be understood that the one-sided limits must agree. Right? So if you're worried about, if you're checking the second point, it might be necessary for you to actually check that the limit as x approaches a from the right side of f is actually equal to the limit as x approaches a from the left side of f. And this gives you L, which is a real number. Right? So that's what has to happen in step 2. And in step 3, the third thing that needs to happen is these two need to exist. They must agree. The above must be equal. So you first have to check, does my function work at the point I'm looking at? Yeah? Okay, that's good. Does the limit exist at the point that I'm looking at? In particular, is it a finite number? Do the one-sided limits agree? If yes, good. The third thing you need to check, do my answers to step 1 and 2, do they actually give me the same value? And if that all works out, if these three things all happen at once, we say the function is continuous at the point. And it means I can sketch the function passing through that point without lifting my pencil off the page. Should be aware, so the definition is one simple equation, but there's some background in what it takes to make that equation work. Okay, so that's the definition. We illustrated it, talked about what it means. What else do I want to tell you guys about? Oh, do I jump into examples right away? How much time do we have? Let's do some examples. I'm going to write down some functions that tell me where they are continuous. Right? Meaning, kind of like the domain situation, use interval notation. So you just described to me, basically in intervals, where the function will be continuous, where it will actually fit this property. And furthermore, if not, why not? Explain to me why it's not continuous. We'll start with those. So you're studying a function, it can be any one of these, and you kind of want to know where calculus has the potential of working, I should probably say. Want to know where this function is continuous. For what x values can I sketch this thing without lifting my pencil off the page and worrying about holes and gaps and asymptotes where I can't touch the function? Okay, let's look at the first one. F of x equals x squared. What would you say? Where is that function continuous? Well, how would you know? So you would check, is f of x equals a be a point in the domain of f, right? In fact, we know what the domain of f is. It's a polynomial, so everything should work. So now I can ask, does f of a, is f of a defined? And the answer is yes. It's defined for all points. In fact, f of a is equal to a squared by the rules of a polynomial. Second, does the limit as I approach a of f of x exist? And the answer would be yes. Because if I take the limit as x approaches a of x squared, by one of our rules from last time, we'll just, well, the domain is everything. There's nothing wrong with just plugging in the number. As your x gets close to the value a, your y values are all going to get close to the value a squared. And then you check, are these two equal? And the answer is yes, of course. That's a squared and that's a squared. So we can say f of x equals x squared is continuous on the interval minus infinity to infinity. It is continuous for all points along the in the domain of the function, which for a polynomial is everything. Another way you might see this phrase being used, so I'll tell you. Whenever that's the case, in other words, we can say f of x equals x squared is continuous everywhere. Right, so that phrase everywhere suggests it's continuous for the entire number length, the entire root length. So that one's kind of a silly example. Let's actually look at okay, what would you say about that function? Where is it continuous? Yeah?
It's discontinuous at x equals 2.
Why?
Because even though you can factor the top to find the limit, that you would still like divide by 0 if you plugged in 2.
Right, so it's not continuous 2 because it breaks the first rule. F of 2 is undefined. Right? Otherwise, the limit as we approach a of the function, x squared minus 4 over x minus 2, is just going to be a squared minus 4 over a minus 2, which will be defined, and it will actually be the limit, and it will actually be the value of the function at that point. So this means f is continuous on, how do you write that down? Yeah.
Negative infinity to 2, parentheses 2 to infinity.
So at all points except 2. So as long as we're not plugging in 2 to divide by 0, you can literally plug in any other number and it's going to be fine. The limit will also be found by plugging in any other number and we'll be fine. So 2 is the only bad point here. What about C? Where I kind of took that function and tweaked it a little bit. So I take the original definition, but I specify that, you know what, we're not even going to consider plugging in 2 here, because obviously that's going to be a bad idea. But so I'm going to define the function to actually output 0 when x is 2. Where is that continuous? Yeah?
Same thing as last one, because as the limit approaches, like the limit of x squared minus 4 divided by x minus 2 approaches 2, it's equal to 4, and so it's like a gap.
Okay, so we know, for similar reasons, other than x equals 2, we're fine, right?
Yeah.
So now let's check what's going on at x equals 2. We know that the limit as x approaches 2 of our function is going to be the limit as x approaches 2 of, how would we find that one quickly? What?
Factor.
Yeah, just go. Factor, or do you get?
Factor the top, so x minus 2 minus x plus 2 divided by x minus 2.
That will cancel. And so we get what?
4.
4. And if I check what is f of 2,
That'd be 0.
that would be 0 by definition. I said when x is 2, the function is 0. And you would notice, not the same. So not continuous. And so we can say it's also continuous on, I don't have space. It's the same answer. So it still doesn't work at 2. Right? It kind of faked us out, gave us some hope. Before f of 2 was undefined, in this case it is defined, it actually gave us a number. The issue is it didn't give us the right number. Right? Notice here, we actually graphed this before, so we already know that it will look like x plus 2, except at the value 2. And so that was that picture. Clearly that has a gap, and that wouldn't be continuous. The picture of this one would look like this. Right? So your function is doing this thing, oh, there's a hole here, can't fill it in, but you jump down here and you fill in this point, and then you continue. Right? You still have a hole, you still have a jump, you still have a gap. Everywhere other than 2, things are fine, but at 2, there's still a break there. So that was C, let's move on to D. Again, same guy, x minus 4. You're not allowed to plug in 2 there, but you can plug in 4 when x is 2. Where is that continuous?
So that just continues from negative infinity to infinity?
Right. This one will actually work everywhere, because you can see what we did was we actually filled in the point in the right location. Right? So that's where our graph was, and then we're like, you know what? It's just this point missing. I pretty much know what the y-coordinate of that point would be. So let's actually fill that in. So now we've bridged the gap. We can just keep going. Right? So it's doing its thing, except at x equals 2, but at x equals 2, I filled in that point with the value 4. And now it turns out there's no gap in my function anymore. There's no hole. I don't have to jump over anything. So again, you can state here other than x equals 2, we're fine. And then you deal with at 2 specifically. At x equals 2, if we find the limit of our function, we get 4. F of 2 is also 4 by definition. And this means it's continuous at 2. Right? Because this works out, that works out, and the third thing worked out. The limit exists, the function is defined, and they actually give us the same value. So it's continuous at 2. So we know other than at 2, it works, and it turns out at 2, it also works, so it pretty much works for everybody. So again, you can have similar functions, but one we can work with while the other one we can't work with, because you can kind of fix something sometimes. We'll talk about these situations as well, when you can fix a discontinuity issue versus not. And you can try a very poor attempt at fixing the problem, or you can do the proper way to fix the problem. You can't always fix the problem, but in this case we could. So this function, as stated, without any restrictions or modifications, not continuous at 2, it's fine everywhere else. This one's still not continuous at 2 because we did a really bad job of trying to help the situation, but here we got it right, and this will actually work everywhere. And so if for some reason I want to do calculus here with this function, it's probably a good idea to redefine it as that function, and then I won't have to jump around anywhere. Let's look at E. Where's E continuous? Take a couple minutes and try to write that one out. And tell me your conclusion, and then we can go through it together. Okay, what's your conclusion? Yeah?
Negative infinity to infinity.
Works everywhere? Okay, justify.
You factor the top equation, you take the limit.
Okay, so you want to take the limit, approaching what point?
X to -2.
Factor at the top, what do you get?
X plus 2x plus 3. Cancel. The limit is 1.
Limit is 1, okay?
F of -2 is equal to 1, so they're equal. Therefore, f of x is continuous everywhere.
Well, you're kind of making a leap there. You don't have all the information for that. Or at least you didn't express all the information for that. Like what you just showed is that it's continuous at 2 specifically. So you do have to kind of make the statement, which we all kind of know, but it's important that you actually show that you've considered it, is that other than at -2, everything is fine. Right, so yeah.
I would never ever in a million years write down other than x equals negative, because like I never did in high school, like we just, that assumption was just, so
Yeah,
like
no,
if I
you
don't.
write it down. Yes, implicit assumptions are problems. Okay, so if we're not at -2, we're fine. At -2, you check these two things, and it turns out that they were the same. So it's continuous at 2, and say therefore, or whatever, f is continuous on -2. Yeah, me telling you to skip this line is kind of equivalent to me telling you to say, oh, if you know the parentheses are there in your head, it's okay not to write them down. It's the same kind of errors that can crop up. You have to be careful that you're considering everything at all times. You're not allowed to be sloppy and, let's not worry about it. Always worry about it. Worry about everything. So, yeah, that one works everywhere. So that function is good. And essentially, the picture here is this function behaves very similar. It behaves like x plus 3. Except at -2, there is a hole, and it turns out that hole happens around the location where the y value is 1, and we filled in that y value at 1. And so we bridged the gap there. So other than at 2, we're fine. At 2, there's a hole, but we filled in the hole in the right position. Yeah.
Just going off of the whole like showing work thing, do you think that in the future you could clarify exactly what you want to see? Because like,
Literally what I'm writing down.
okay, because a lot of times I think like I interpret like sometimes you write things on the board like for clarity's sake for teaching purposes and not necessarily for work.
Yeah, usually I write that in red.
Okay, because like it's just
Yeah.
like on the quizzes you collect 0 work, and then on the midterm and the final and the other exam you're gonna collect our work.
Yes.
And I would just hate to like all of a sudden lose 20 points on the midterm because I didn't show what you wanted to show
Yeah.
because I didn't know that.
But I literally tell you. So I'll tell you it's not okay to leave this out. Or I'll
Okay.
tell you. It's pretty much kind of do as I do kind of thing. The way I write down a problem on the board is how I expect you to write down a problem. So you can literally just mimic me the whole time. You'll be fine. If there's something that I want to clarify for teaching purposes, I'll usually write it in another color. And yeah, and if at any point anything is not clear, you can ask me, do I have to write that down or is it no, and I'll tell you, oh yeah, you can skip that. Yeah, I'll tell you. If anything's not clear, you just ask and I'll tell you, okay, it's not important for you to write that. But usually how I write out a problem is how I expect you to write it.
Okay.
I'm not going to be sloppy here and then expect you to be perfect. Right?
Gotcha.
I don't think that's fair. And you're allowed to use that against me. So if at any time I grade you and I'm like, you didn't show enough work here, and you'd be like, yeah, well, in class, you did this, and you can show me that you did what I did, I'm like, okay, fine, I'll give you the points. You can use it against me. What can we do in 3 minutes? We can do a lot in 3 minutes. Let's look at a couple more examples. Let's look at y equals the function sine x over x. Do I want to do that? Let's just do sine x over x and make a conclusion about that. So if we want to determine whether this is continuous, I would say something like other than x equals 0, we're fine. Because I would simply just find the limit by plugging in that value. At x equals 0, f of 0 is undefined, which means f is not continuous at x equals 0. This means f is continuous pretty much anywhere except x equals 0. So I'll say it's continuous on minus infinity to 0, union 0 to infinity. So I ask you to show this is continuous. That's kind of what you would write down. Here's a follow-up question. Can we fix this? Could you somehow go from a situation where there's a problem to a situation where there's no problem? I don't care what point you're at, everything's going to be fine. Yeah.
Well, like if we write it like we were before that, like as a piecewise function,
Yeah.
and you answer the fact that, like at 0, x is, no, at 1,
So we
X.
define,
is equal to 0.
so f of x equals, you change to a piecewise function, so you'll say, okay, leave everything as is, except at 0. At 0, what would you say?
1.
Set it equal to 1. And then, in step 2, we'd be like, well, the limit as x approaches 0 of sine x over x, we know that is 1, and f of 0 is 1 now by definition. This means f is continuous at x equals 0, so f of x is continuous on the entire real line. It's continuous everywhere. You could literally fix this issue by plugging in the number at a single point, right? By the way, this graph looks something like this. And there's a hole over here. There's a hump that's coming up. Yeah, so in other words, what I want to introduce to you is this notion. Whenever we can do this, we say we had a removable discontinuity. So there was a bad point where the function didn't really work out very nicely. However, if you can literally fix it by just filling in that point, or a finite number of points, we say we had a removable discontinuity. Right? So these are discontinuities that can be fixed by redefining f at a finite number of points. So if I can literally fix all our problems by taking a finite number of things and filling them in, I say these discontinuities were removable. There are ones that are non-removable, they're called essential discontinuities. We'll write those down next time. But sometimes you can fix issues, but you have to be aware that the issues are there in order to fix them. We'll stop there for now, and I will see you guys on Friday.